Stream 00 Alpha, cleared to Irish intersection. Hold west on Victor 134. 5 mile legs, left turns. Expect further clearance at 1425. Anticipated
Cessna 4905, Kilo Alpha, Laramie 15, 17,000, Cheyenne 25.
United 327 Heavy, descend and maintain 7,000, cross Henderson VOR at or below 1.
Although the departure and arrival phases of instrument flight are often considered the most demanding, the en route segment can test your IFR skills just as easily. You must be able to combine your ability to control your airplane accurately using instrument interpretation with precise navigation skills, so your exact position is never in doubt. The Jeppesen en route charts are designed to simplify instrument navigation. Whether you're following a route you've flown hundreds of times or one in which ATC has just directed you to an intersection to enter a holding pattern. In this program, we'll look closely at the detailed information printed on the en route charts. By understanding the exact meaning of each symbol, you'll be able to rapidly and accurately interpret all the data shown. Let's begin by looking at the low altitude en route charts, which are used for flight below 18,000 feet MSL. Jeppesen prints several low-altitude en route charts that cover the United States. There are a number of ways to locate a particular chart or find a specific location or route. For example, on the front panel is a chart index. The heavy black border surrounds the coverage region of the chart in hand. U.S. low 19 and 20 charts provide en route information for part of the central United States. Major cities are shown to further help you with chart selection. Cities shown with bold type and gray shading depict terminal areas which have a published area chart. Time zone boundaries are identified by a series of T's on the chart index. This example shows the division between the Mountain and Central time zones. The front panel also provides the formulas for converting daylight and standard time to universal coordinated time. Here you can see the conversion formulas for both Mountain and Central times. Above the chart index is the effective date. You should not use this chart before 0901 Zulu on 11 September. If the chart does not have a specific effective date, it states effective upon receipt. In addition, the front panel contains a listing of major changes which have occurred since the last printing of the chart. On the back panel, you can use a feature called ZigDex, or Zigzag Index, to locate major cities. For example, Goodland is located on panel 6 of the U.S. low 19 chart. To find the city, open the chart to panel 6. The en route charts are designed so you can follow your flight's progress by turning the panels like the pages of a book. This convenient feature helps in cockpit management since it is seldom necessary to completely unfold a chart. Generally, the back panel also contains a listing of special use airspace and, if applicable, part-time terminal airspace hours. These will be discussed later in this program. The bottom portion of the front panel is the City Location Guide. This is an alphabetical list of cities with IFR airports only, and their corresponding locations on the chart. For example, Goodland is located on Panel 6, Section C. When a chart is opened to a particular panel, which in this case is Panel 6, it can be further divided into 4 sections by imaginary horizontal and vertical lines. These sections are labeled in the top and bottom margins as A, B, C, and D. The panels and sections are useful location identifiers. As previously noted in the City Location Guide, Goodland is located on Panel 6, Section C. Now let's move to the chart itself. We'll begin by looking at some basic methods of airspace depiction. Controlled airspace is shown in white. Within controlled airspace, ATC provides separation for IFR traffic. Uncontrolled or Class G airspace is shown in gray and extends upward to 14,500 feet MSL. Although high-altitude jet routes pertain to flight at and above 18,000 feet, they are printed on low-altitude charts for orientation. These routes, which are shaded green, help you transition from the low-altitude structure to the high-altitude structure and back again. Special use airspace is shown in green and magenta and is designated for use whenever aircraft activities require airspace operational limitations. For example, a restricted area is outlined with magenta diagonal slashes. The identifier, affected altitudes, times of activity, and controlling agency are shown. If space is limited, this information is printed either adjacent to the area or will be found on the front or back panel in the section entitled Special Use Airspace. This particular restricted area is R4806E. It uses the airspace beginning at 100 feet above the ground and has an unlimited ceiling. The area is active from 0500 to 2000 local time, Monday through Saturday, and other times by NOTAM dissemination. Los Angeles Center is the controlling agency. Green diagonal slashes surround a warning, alert, or MOA airspace. This MOA has a floor of 100 feet AGL and extends up to flight level 180. The ball flag indicates that there is additional information about the area contained elsewhere on the chart. Here it states to contact Nellis Control or the nearest FSS prior to entering the MOA. Now let's look at the types of controlled airspace that are found in terminal areas. An airport surrounded by Class C airspace is enclosed by a shaded blue outline with a series of Cs included. The upper limit of the Class C airspace is shown next to the area. However, some Class C airspace areas have shapes that do not conform to the standard circular dimensions due to their proximity to high terrain or other types of airspace. Class B airspace areas are depicted by a shaded magenta outline with a series of Bs included surrounding the primary airport. This symbol represents the lateral boundary for the upper limit of the Class B airspace. The altitude for the upper limit is shown to help you select an altitude to overfly the airspace. You'll find a detailed portrayal for each sector on the Class B airspace charts that accompany your area charts. The locations of area charts are identified on en route charts by shaded gray dashed lines that surround the charted region. These charts use the same symbology as en route charts, but their scale has been adjusted to provide more detail. You should refer to the area chart if your departure or destination airport is within the boundary shown on the en route chart. The lateral boundaries of the surface area for Class D and Class E airspace are depicted with a blue dashed line. The class of airspace will be indicated within the parentheses along the boundary. An asterisk indicates that the hours of operation are found on the back panel in the section entitled Part-Time Terminal Airspace Hours, Class CDE. In this example, the airspace is Class D. Effective times are 0600 to 2200 local time. The airspace becomes Class E at other times. Surface areas of controlled airspace where special VFR is not permitted are depicted with small magenta dots, such as here at Cleveland Hopkins International Airport. There are many items printed on en route charts to help you maintain orientation. For instance, the green dashed line, which shows 2 degrees east, depicts the magnetic variation for this region. Latitude and longitude lines are shown on the chart by thin green lines, such as 39 degrees north latitude and 91 degrees west longitude. A distance ratio at the top of each chart shows you the scale. In this case, 1 inch equals 15 nautical miles. A nautical mile scale is provided along the top of each chart. Beneath the chart number, it is noted that the Lambert conformal conic projection is used to minimize distortion in transferring a section of the Earth's curved surface onto the flat chart. With this type of projection, a straight line on the chart represents a great circle route, which is the shortest distance between 2 points along the curvature of the Earth. Another item used to help with orientation is the set of wings with a north barb pointing to true north. Light blue bands portray areas where en route charts overlap one another. In this instance, the low 10 and low 11A and 15 represent the exact locations where those charts overlap this chart. This note refers to an area which is covered elsewhere in an inset. If the inset is on a different chart, it will be noted. In this case, the inset provides you with the en route data you need, covering an off-the-chart area over a body of water. Let's continue by looking at airport symbols and related information. Civil VFR airports are identified by small green circles with cogs. Military VFR airports are shown by smooth green circles. Civil IFR airports are shown by small blue circles with cogs. And military IFR airports are shown by smooth blue circles. Both civil and military seaplane bases are charted with an anchor inside the appropriate symbol. Heliports are labeled with an H. Notice again that IFR airports are in blue, and VFR airports are in green. Civil airports have cogs, and military airports are smooth. The airport symbols on en route charts are divided into 2 main categories: those showing airports with a standard instrument approach procedure published by Jeppesen, and those without. When an airport has a standard instrument approach procedure, the airport location is labeled in all capital letters, and the lettering and symbol are in blue. As you might remember, this information is also found on the bottom front panel of the appropriate chart. The approach charts are indexed under this name. The airport's name is also provided when it differs from its location. In this example, Hale County Airport is located in Plainview, Texas. If applicable, frequencies for FSS, ATIS, ASOS, and AWAS are listed above the airport location. Below the airport name is the Jeppesen Nav data, or ICAO airport identifier, along with the airport elevation and the longest runway length to the nearest 100 feet. In this example, by adding 2 zeros, 60 equates to 6,000 feet. Locations of airports without published instrument approaches are indicated with lowercase letters, and the lettering and symbol are in green. These VFR airports also contain an airport identifier, airport elevation, and runway length. An S indicates a soft surface. The absence of an S means it is a hard surface. Jeppesen uses various symbols to show navigation aids. For instance, a VOR is presented as a compass rose with a thin barbed line that orients the symbol to magnetic north. This barbed line allows you to measure the magnetic bearing of any course by using a Jeppesen IFR en route plotter. DME and TACAN facilities are portrayed by serrated circles. Both of these stations provide slant range distance information. In addition, TACAN facilities provide continuous bearing information for suitably equipped aircraft. When a VOR station is combined with a TACAN or DME facility, the resulting VORTAC or VOR DME is shown by combining the 2 symbols. NDBs are marked by a series of 3 concentric green dotted circles with a thin barb pointing to magnetic north. The frequency, identifier, and Morse code for the NDB are listed below the facility name. A localizer facility is shown on the en route charts only if it performs an ATC function, such as identifying a fix, and is noted with a half-feathered arrow. In this case, Kirk is the intersection. The localizer frequency, identifier, Morse code, and the inbound course are shown. Now let's look at the identification and communications data that coincide with the NavAid symbols. When a NavAid is an airway or route component, the identification is given in a shadow box. In this example, the frequency for the Monroe Vortac is 117.2 megahertz. The station's three-letter identifier, MLU, and the Morse code ID are also shown. The D preceding the frequency indicates DME capability, and the L in parentheses represents low-altitude NavAid operational range. The information for a NavAid which is not part of the airway or route structure is not enclosed in a box. For instance, the VOR located at Higginsville Industrial Municipal Airport is used primarily for terminal operations, as depicted by the T in parentheses. The navigation information for a TACAN or DME station which is not frequency paired with a VOR is shown next to the symbol. The frequency of 111.6, shown in parentheses below the TACAN channel, provides civilian reception of distance information. The NavAids at Randolph Air Force Base show a similar situation. Although the VOR and TACAN appear to be co-located, they are actually separate NavAids as shown by the notation. The VOR frequency of 112.3 will not provide distance information. The frequencies for en route radio communications are listed across the top of the NavAid box. If voice capability is not available through the NavAid, only the Vortac navigation frequency is shown. The number shown directly above the box is the frequency available to communicate with the flight service station. Radio frequencies, which are in the 120 megahertz range, are shown with the first two digits omitted. Wichita is the FSS you can contact. A G next to the frequency indicates the flight service station guards or receives on that frequency. They transmit through the Anthony Vortac frequency of 112.9. En route flight advisory service is identified by the WX abbreviation. You can contact Columbia Flight Watch on the designated frequency of 122.0. If a star precedes any frequency, it means that service is not continuous. For example, Flight Watch service normally is provided between 6 a.m. and 10 p.m. local time. Since the purpose of Flight Watch is to gather and distribute current weather information to en route pilots, the Flight Watch specialist will not open, close, or file flight plans. Availability of another type of en route weather service is shown by a HIWAS designator. HIWAS stands for Hazardous In-Flight Weather Advisory Service and is continuously transmitted over the VOR frequency. HIWAS broadcasts contain weather advisories, including severe weather alerts, SIGMETs, AIRMETs, and urgent PIREPs. The letters TWEB signify that transcribed weather broadcasts, or TWEBs, are available through this facility. Selected VORs and NDBs broadcast continuous weather information over the NavAid frequency. TWEBs consist of recorded tapes giving local weather conditions, along with general forecast and route information for the area. Although the information varies, the broadcasts generally contain route-oriented in-flight advisories, winds aloft, current weather reports, NOTAMs, and weather notices. The small encircled dot shows another en route communication service. The Great Falls FSS transmits and receives on 122.45 at the Miller Peak Remote Communications Outlet, or RCO. The black ticked line signifies the boundary between Salt Lake City Center and Seattle Center. You should expect a frequency change near this line. Boxes containing ARTCC frequencies can also be found throughout the charts. The next area we'll look at is how airways and their associated navigation components are shown on en route charts. Victor airways are formed by radials extending from VOR, VORTAC, or VOR DME stations. The airway center line is identified by a solid black line. The VOR radials forming the airway are labeled next to the NavAid symbols. The standard airway width of 8 nautical miles is maintained to a point 51 nautical miles from the NavAid. If the airway extends beyond this point, the controlled airspace expands to include the areas which diverge from the NavAid at angles of 4.5 degrees. Victor airways are identified by a number that indicates their general direction. Even-numbered airways are usually oriented in an east-west direction. Odd-numbered airways are generally oriented north and south. When more than one airway shares a common route segment, all identification numbers are shown. When special information is needed and space is limited, a circled letter, called a ball flag, directs your attention to a note printed on the panel. This ball flag shows that a segment of Victor 55 does not exist when the Devil's Lake East MOA is active. All airway distances are expressed in nautical miles, unless otherwise noted. An enclosed number indicates the total mileage between NavAids. Mileage figures not enclosed, such as 27 and 14, indicate the distance between intersections, VORs, and mileage breakpoints. In this example, the distance from Farmington to DD intersection is 27 miles, and from DD to Cape Girardeau, 14 miles. The total distance from Farmington to Cape Girardeau is 41 nautical miles. Mileage figures not only help you compute your total trip distance, but also assist in determining the changeover point where you should switch from one NavAid to the next. Unless otherwise specified, the changeover point, or COP, occurs halfway between the NavAids. When the changeover point is not at the midpoint, it is shown with this symbol. In this example, the COP is 59 miles from Twin Falls VORTAC and 90 miles from Salt Lake City VORTAC. By changing over at the recommended point, you will continue to receive reliable, accurate NavAid signals. The location of the changeover point can affect the shape and therefore the controlled airspace of an airway. For instance, if an airway is 100 miles long and the COP is located in the middle, then the width of the airway is 4 nautical miles on either side of the center line. By moving the COP closer to one facility, the controlled airspace changes due to the 4.5-degree angle that diverges beyond 51 nautical miles from the NavAid. A mileage break symbol is most often associated with a course change where an intersection is not designated. Where a mileage break has been unnamed, Jeppesen has assigned a nav data database identifier. Since these identifiers apply only to the Jeppesen database, the identifier should not be used as a reporting point for ATC or when filing a flight plan. An arrow along an airway points from the NavAid designating a reporting point. In this example, Toddy intersection is defined by the 167-degree radial from Hugo VORTAC and the 081-degree radial from Pueblo VORTAC. When the radial that defines a fix is not designated as a flyable route, it is indicated by a long, thin arrow. Orway is defined by the intersection of the 133-degree radial of Colorado Springs and the radial which defines Victor 10, 244. Where distance measuring equipment can be used to define a fix, a D with a solid arrow is shown with the mileage being determined by that listed along the airway. In this case, the DME distance from Pueblo Vortac to Orway intersection is 18 nautical miles. If there is more than one fix along the airway, the mileage immediately follows the D. Here, the distance to Toddy is 38 nautical miles. Unless you're in radar contact, IFR position reports are required at certain points along the airway. These points are referred to as compulsory reporting points and are indicated by solid triangles. If the compulsory reporting point is at a navigation facility, the solid triangle will be part of the facility symbol. Open triangles depict non-compulsory reporting points requiring a position report only when requested by ATC. Intersections are associated with reporting points and provide a positive means of establishing your position. The name of the intersection is usually 5 letters and is shown near the fix. In the case of Hardy intersection, note that the holding pattern includes a speed restriction. In some situations, the nav aid forming an intersection is located off the chart or at a considerable distance from the intersection. In other cases, the thin arrow identifying the fix might be hidden by other information. When this happens, the 3-letter identifier, radial or bearing, frequency, and distance, if appropriate, are shown along with a portion of the intersection identifier arrow. Where the nav aid forming an airway is located off the chart, its name is shown along the edge. When the nav aid helps form an intersection along the airway, or the changeover point occurs on the chart you're using, the nav aid's frequency and identifier are also shown. For example, Wormy intersection can be identified by the 30 DME from Llano Vortac along the 110-degree radial. Now let's review the various en route altitudes. Each designated airway in the continental United States is charted with a minimum en route altitude, or MEA, that has been established for 2 primary reasons. First, it guarantees obstacle clearance, and second, it indicates the lowest altitude at which you can expect adequate navigation signal reception. In addition, you can usually expect adequate communications at the MEA, although it is not guaranteed. When you're on an airway, the MEA normally provides a minimum of 1,000 feet obstacle clearance over non-mountainous terrain and 2,000 feet in mountainous areas. The minimum en route altitude is shown below the airway identifier. On some airways, the MEA is different depending on the direction you're flying. For example, if you're flying west from Stano intersection, the MEA is 12,000 feet. However, if you're flying eastbound from Flood, the MEA is only 9,000 feet. Although you can typically expect navigation signal reception at the minimum en route altitude, a broken bar symbol indicates a possible gap in the navigation signal even if you maintain the MEA. This break usually occurs for only a very short distance. When the MEA changes at a location other than a nav aid, a break in the airway is shown, and small bars are placed across the airway centerline. Notice that the MEA is 4,300 feet to the west of Safer intersection and 3,400 feet to the east. When rising terrain requires that you climb to a higher altitude before reaching a fix, a minimum crossing altitude, or MCA, is established. The MCA is shown by an information grouping consisting of the Victor airway number, the crossing altitude, and the direction of flight. When a minimum crossing altitude occurs at a nav aid, it is identified with a numbered ball flag. The applicable information is listed elsewhere on the same panel. In addition to an MEA, some route segments also provide a minimum obstruction clearance altitude, or MOCA. The letter T for terrain is shown with the MOCA to distinguish it from the other types of altitudes. The MOCA meets obstacle clearance requirements, but only provides reliable signal reception when you're within 22 nautical miles of the navigational facility. In a few cases, maximum authorized altitudes, or MAAs, are specified. These normally occur below special use airspace or when two VORs transmitting on the same frequency could cause signal interference at higher altitudes. They are indicated by the letters MAA, followed by the applicable altitude. At some intersections or fixes, terrain can interfere with the reception of the nav aid which forms the fix. Where an altitude higher than the MEA is required to identify the fix, a minimum reception altitude, or MRA, is designated. The next area we'll cover is the high-altitude charts, and some of the items which appear differently on them. Since these charts cover portions of the Canadian and Mexican high-altitude structure, information about airspace variations is provided on the front panel. A primary difference between high and low-altitude charts is that nav aid information is presented in a different form. For instance, the compass rose that usually surrounds VOR stations is not shown. However, the magnetic north barb is printed for use with the Jeppesen IFR en route plotter. As with low-altitude charts, a shadow box is used to identify a nav aid that is part of the en route structure. However, the shadow is only on the right side of the box since the geographic coordinates for the nav aid are listed below the box. Off-airway nav aids are indicated by omitting the shadow from the frequency box. Frequencies for HIWAS and TWEEB, along with flight watch information, are included on high-altitude charts where available. Jet routes are shown in the same basic manner as Victor Airways. If the jet route designator is shown inside an arrow, such as J110, the airway is a preferred one-way route. If an effective time is also included, it is only one way during that particular time. Otherwise, it is a two-way airway. MEAs are only shown on high-altitude charts when they are higher than 18,000 feet. Sometimes a nav aid or intersection appears to be part of a jet route, when in fact the route bypasses the fix. The letter D designates a preferred IFR direct route which is not part of the jet route system and is 130 nautical miles or more in length. On high and low altitude en route and area charts, Jeppesen also provides minimum off-route altitudes, or MORAs, located within grids formed by lines of latitude and longitude. In this example, the number 26 represents a grid MORA of 2,600 feet and is an altitude which will provide obstacle clearance during an emergency descent. If the highest natural or man-made object within the grid is a non-mountainous area, the minimum off-route altitude provides you with at least 1,000 feet of clearance. When the highest object or terrain is in a mountainous area, 2,000 feet of clearance is provided. Additionally, for terrain awareness, generalized terrain contours are depicted on selected area charts. Within contour intervals, some, but not all terrain high points may be included along with their elevation above mean sea level for use as additional reference. DME arcs are shown for situational awareness. On high-altitude charts, the lines of latitude and longitude, as well as the magnetic variation, run through the entire chart. Flight in the instrument environment challenges your piloting skills continuously. Jeppesen and route charts provide the navigation and communication data needed to meet the challenge. However, their effectiveness depends on your correct interpretation of the information portrayed.